Okay, so I guess I'll start. Yeah, my name's Roland. Fun fact, I was a CMS Wrangler myself, so go Wranglers. I went to Calhoun High School and all that too. I work at Texas Instruments. My job is an analog design engineer, and I guess we'll talk more about that as we go on. And I live here in Dallas, and my hobbies are gardening and I like skateboarding and mountain biking, and trying to stay active. Sitting in the chair all day, you need to stay active, right? So.
Yeah, which is not very different from what you guys are interested about nowadays. I guess we're not very far away from our school years either, right? We'll only be in the industry. I'm being in the industry for 3 years, and Roland has been with TI for 6 years. That's where we spend our whole career at. I'm Will. Originally, I'm from China. 4 years ago, I came to the U.S. for my master's education at University of Florida, and then a year after that, I was hired into TI. That's where I spent this last 3 years. I used to be an analog design engineer. I designed analog circuitry that goes into the chip, and the chips that we can use a lot of chips in a whole system like the cell phone, the iPhone that you guys are seeing in here, and a lot of other stuff. Then right now, I just switched job. Right now my job is a system engineer. Instead of figuring out how to implement a chip, my daily job is to communicating with the customer to see if our microchips are a good fit for their system.
All right, so I guess this is, we're supposed to help give you guys an introduction to STEM, because I think you're supposed to choose your major sort of in high school. So I was going to give an introduction to electrical engineering in general. I mean, we both studied electrical engineering, and that's our job, but there's a lot of different areas in electrical engineering. We're going to talk a lot about microchips and what TI does, and that's a big part of electrical engineering, but there's several other parts. In general, microchips are, you don't buy them yourself, right? They're a component in some other system. But there's a lot of technology and a lot of engineering that goes into making these subsystems. So there's a lot of engineers and scientists that work on chips, but there's other engineers that study electrical engineering that, say, design systems, like, say, Apple's iPhone. Apple doesn't make every component in there. There's hundreds of components in that phone, and they come from lots of different companies. I mean, for example, TI, one of their main functions is they're part of the touchscreen technology in the iPhone. So I mean, whenever Apple was coming up with it, they came to TI and asked us to help them develop this technology, and we did. And that's a good example of a product that you guys use every day that that TI was involved with. So this is more like on the hardware side. You're making circuits that deal with currents and voltages and physical properties. But then since computers are electrical machines, a lot of programming and digital stuff came out of electrical engineering. So if you study electrical engineering, you can do something like digital signal processing, and a good example of that would be Siri, right? Your voice, gets converted into a digital signal, a string of numbers, and you can do math on those numbers to do lots of different things. In this case, they use a type of math called statistics to figure out whenever you say something, what word you're saying. And electrical engineers work on those kind of algorithms and those kind of systems. And this is all kind of small. This is small stuff and microscopic.
I have some samples that I can show you guys. So these are the microchips that Roland was talking about in here. You can figure out the size, how small the sizes are. Comparing to the fingertip. And I'll let you guys pass around these samples in here. Just be a little bit careful because it's going to fall out very easily.
So you can see that. I guess you've probably seen the little black squares with little feet sticking out of it. This is basically just one of those with the top removed, so you can actually see the die and the little wires that stick onto the pins. And there's little bitty gold wires.
Can humans put those together, or is that?
No, they used to actually. There's an interesting documentary on Netflix about how Silicon Valley got started. So if you're curious about that, check that out. No, everything's done automatically
nowadays. And so you guys are seeing the samples of microchips in there, and basically there's different steps to make a microchip like this, right? they are made from what we call this, a wafer. And you guys probably are seeing the repetitive pattern in here. Basically, each one of the squares is a die that can go into the package and form a microchip like this. And there can be thousands, tens of thousands of dies in each piece of the wafer. I'll probably start from there so you guys on the back can see it.
So we'll talk more about chips, but I was just saying that other things that electrical engineers do, and something that will be, of more importance in the future as we, start having more renewable sources of energy, is, high power engineering. This is, figuring out how do you, if you have some windmills that are offshore, 100 miles offshore, how do you get that energy back to power the city? There's a lot of thought and a lot of engineers that are needed to figure that kind of stuff out. So that's one branch of engineering. Another branch is, doing controls. And basically, how does a helicopter stay in the air? It's not just the guy exerts his will to keep it there. There's a lot of what we call, electronic control systems that stabilize it. And electrical engineers are trained, with the mathematical analysis and whatever that goes into designing control systems. And then also, electrical engineers work in the field of communications, which is, the internet, or how to the radio, or any type of electronic communication system. How do you modulate it? How do you turn your voice into a little signal that can go from your cell phone over to a tower half a mile away? And there's a lot of different subsystems there, and a lot of different things that you can do as an electrical engineer to kind of contribute to that.
Yeah, and feel free to stop us whenever you have a question. Okay.
So we work for TI, so we're putting our TI plug here. But so you probably know TI because of the calculators that you probably use in your math class, and that is a important product for us. But it's actually a small part of our business. Nowadays, our main business is making microchips for lots of different applications: automobiles, cell phones, factory equipment, just about anything you can think of. Interesting fact is that Texas Instruments, Jack Hilby, who worked at Texas Instruments, invented the integrated circuit. He invented the microchip. And that's kind of like one of the key inventions of our century, and has led to the technology age. And that was invented right here in Dallas at Texas Instruments. So that's kind of interesting. So like I said, I'm an analog design engineer, and I guess the term analog, just the world is analog, right? You hear, how do you turn your voice into something, into a file on your computer, a list of numbers, right? The list of numbers, that's digital, right? Digits. Anyway, so anything that deals with the world, how do you, if you want to measure the temperature, if you want to record sound, if you want to record video, if you want to make a motor turn, if you want to make a light shine, any of those things, that's basically analog. And the interface between other physical quantities, motion, sound, pressure, and electrical quantities that can be processed by a computer, that's what analog engineers deal with. And I guess by a design engineer, I guess the way you want to kind of explain how you would develop products?
Yeah, TI is a big organization all over the world. We have different branches all over the world. Basically, I'll give you guys a brief introduction of how the semiconductor industry, the whole product cycle works. First of all, we're an engineering company. We need to go out to our customers to figure out what kind of problems they have. For example, the new Apple cell phone, probably the Apple people are working on iPhone 7 or the iPhone that's going to come out in a year or two already, right now. So we need to figure out what kind of problems they have. They'll probably say, we need to improve our current design on our touchscreen chip that can interpret, where is your finger is at on the screen, right? So first step, we would go out there to talk with our customers, figure out what kind of problems they have, and then we figure out a solution, and we come back. We talk with our design engineer to figure out how we can implement our solution, and that's Roland's job to design the whole circuit, the whole chip, right? And after we deliver, probably 6 months or so, Roland will be done with a chip design, and then we'll deliver our design to our fab. The fab can be in Richardson or in some other countries in the world, in Asia, in Europe, and then probably the cycle will be like 2 months. We'll have the chips ready, and the next step is we need to have those chips tested, so that we'll make sure that those chips work, and we won't have unhappy customer when we sell them to our customer, to Apple, for example.
Yeah, so there's a lot of different jobs that occur along that line of things, ranging from very, if you're a people person, you like to work with people, you'd probably rather be out in the field talking to customers, trying to win new business. If you're kind of in the middle, like Will, you like talking to people, but you also like digging in on some technical stuff, trying to learn, solve technical problems. That's the kind of job Will does. My kind of job is more really digging into the problem, trying to figure out, hey, this is the kind of circuit we need to make to do that function that you're trying to do, and maybe it's never been done before. And that's one thing that's kind of interesting about engineering is you're not just repeating a process. You're not just following a checklist. You have kind of an end goal, and you have some ideas about what you might be able to use to solve the problem, but it's not defined. You have to come up with how to solve it. It's not that, we're not manufacturing something. We're giving instructions. We're telling what needs to be manufactured.
Okay.
I was just giving some examples of some projects that I personally worked on at TI. I've been working most of my time with automotive applications, and this is an area that's really exciting now because cars have to have, governments around the world are asking automotive manufacturers to make their cars more efficient, use less fuel, use different types of fuel. So that trend is going on, and also people are wanting more technology. They want their car to drive itself for them. So all of these systems are basically creating demand and creating needs that electrical engineers need to solve. How do you do all this? So one of the projects that I worked on was, is used in this Tesla car that you're probably familiar with, with their next generation, infotainment platform, as they call it. And I've done some other chips, for less glamorous parts of the car, like the transmission. You don't really realize it, but your whole car is, full of computers. Like, the accelerator pedal doesn't go to anything. It just goes to a little switch that simulates what it would do, and the computer reads that and sends it to another computer that tells the engine how to work. So there's computers all over the place. Your transmission, a little shifter, it doesn't actually shift anything. It's just a decoy. It just tells you, the transmission controller, what you're doing. It's just like a joystick on a video game. And Will and I have also worked on some parts for some devices that you might be more familiar with, and that were kind of especially satisfying. Like right now, one of the chips that we finished a few months ago is ramping in. It's in these new Samsung smartphones that you might be familiar with, and some other types of devices that you would never think had electronics in it, like a pressure sensor that just kind of looks like a bolt, but actually embedded inside of that is some circuitry that reads the sensor, that has a little microcomputer built into it that can calibrate it to make it more accurate, and then output the signal that another system can use to, if it's trying to check the pressure of your engine or something like that.
Yeah, so probably you guys now is familiar with the idea, the whole system, like a Tesla car or even your iPhone, is pretty complex, and it has multiple functionality, right? And each one of the small chips is probably in charge of a specialty, a kind of functionality. And here I have a perfect example of how we can make the conventional thing more smart. So this is a smart basketball. What is special about this basketball is that there's chip inside of it, and what those chips do is that it takes sample of the physical movement of this ball. For example, how fast it travels, how fast it spins. If you were to shoot around, what is your curve like? Something like that. It takes those data, and then there's also another chip inside of it that is in charge of the communication, right? It has the Bluetooth capability built into it so that it can talk to your cell phone or your laptop. And your laptop, there's a software that is capable to take in those data and then analyze it do a report so that you know, is there any problem in the way that you're dribbling the ball or you're shooting the ball? I think it's very popular in the professional athlete field as well as in our daily lives. You know, the professional footballers or basketballers, they use this kind of technology to improve their skills, right? There's also a pretty cool chip inside of it. As you think along, you know, it can do this much functionality. What powers it? There's a power chip inside of it. You know, I'm not sure if you guys are familiar with the idea of wireless charging, but there's a wireless charging chip in here. You know, here is a charging port and a dock that comes with it. You know, you can sit this ball onto this pad. It's a power pad, and it can be attached to our wall outlet, and you just kind of align this charging spot in here, and it automatically picks up the power that is delivered by this mat.
Yeah, that's a pretty cool example of some technology that TI helps enable.
It's actually it's a $200 to $400 ball, depending on what kind of functionality you have. It's actually cheaper than iPhone on Samsung phones, right? So I think, what's that? Not necessarily, probably. Probably your laptop will do its job. Yeah,
How
but
much will a laptop cost?
probably $300, $200.
Yeah, what Windows power?
Yeah, it'll probably it could get cheaper. I mean, that's just kind of like almost a prototype. I mean, I guess it is an end product, but it's just illustrating a lot of different things. Like there's some gyroscopes in there that sense how it's spinning, how it's moving. There's circuitry that TI designed that reads those gyroscopes and processes it. I'm sure there is, but I mean that's another aspect of it. How do you make these systems reliable? Right? If you make a chip, for example, in your car, in your braking system, that's a life or death situation. And so there's a lot of analysis that we put in to make sure that our chips are 100% bulletproof. And you can do a similar thing. Obviously, with the basketball, the worst case is your basketball is going to stop working. Yeah. But that's another. There's a lot of engineering that goes into making it reliable.
Yeah, and I guess it's not like groundbreaking kind of new technology. I think the same kind of technology or similar kind of technology has already been used in one of the World Cups, if you guys remember. There's chips that going into the soccer balls that tells us or tells the referees if the ball is or if the ball is passed when a forward player is offside or something.
To detect offsides or something. Yeah. Does anyone else want to look at this?
Wait, what?
I guess we're doing kind of Q&A now. I guess there were some other things. Yeah, I guess so. I guess we've given you some descriptions of the kinds of systems that TI does, and some of them you're very familiar with on a daily basis, like on your phone. And it sounds there's a lot of complicated stuff. So maybe you're wondering how do you get into this? You have to be like Albert Einstein or something? Well, no. So my background, I went to Coppell High School. I went to CMS West, and I was an average student. I wasn't like this genius math class kid or whatever. But I took all of the classes that were available and just gave it a try. And I encourage you guys to do the same. And I went to basically to be an engineer, you pretty much have to have a bachelor's degree. And there's a lot of people at TI that only have a bachelor's degree. For example, our CEO, that are very successful. But a lot of us do go on to get a second, some other, either a master's degree or a PhD to do a more specialized area. I guess I showed you earlier all those different fields of engineering. You can't be good at all of them, right? You can hardly even be good at one of them. So in general, if you want to focus on one, like we do microelectronics, we probably specialize, we just studied microelectronics for like 2 years straight, and that's what I did for my master's degree. And I guess another cool thing is, when you work in a field like engineering, there's a lot of companies and institutions that are willing to, they want to help you, they want to enable you so that you can work for them and innovate for them, so they're willing to give you money. So, like when I went to school, Texas Instruments, paid for me to go on an exchange program to Denmark, and I got to have some incredible experiences, and a lot of my fellow students had similar experiences. And then I guess before we get to the questions, the other thing was, okay, so this is a lot of work. You have to take a lot of math classes. What can you expect to get paid if you're an engineer? So I just picked this off of the, there's this website called Glassdoor. You'll probably want to see that. You'll probably be more interested in that whenever you start job hunting in the future. But anyway, for reference, I looked on Wikipedia and it said that in Coppell, typical family income, your mom plus your dad's about $107,000. And a typical man makes about $76,000. And just to give you a reference, a typical engineer, I think the average overall at TI is about $85,000. And then on some of the specialties, you can make more. And then, of course, if you excel and become a manager and all this kind of stuff, you can make more money. So that's that. So I think we'll just take questions now. If anyone has anything to ask.
Okay, so questions.
So as we're 7th graders and kind of beginning to explore ideas, what do you have in terms of, I'll throw a few at you, recommendations in terms of going into, if you're interested in science and engineering and so forth, where you maybe see a big company like TI, who's a large employer worldwide, evolving, and then maybe touch a little bit on what you experience day to day in your jobs each, so that gives us a little better flavor too.
Yeah, our engineering job, the schedule at Texas Instruments, it's pretty flexible. It doesn't mean that you don't have to come into the company 8 a.m. and get off work at 5 p.m. something like that. We usually work on a workload basis. For example, if I have multiple projects going on, they need a lot of input from me. I'll probably work for 12 hours a day, 5-6 days a week or something like that. And when the workload is lighter, I can probably work less hours. That's pretty much what the industry of semiconductor dictates us to do. Our electronics have their own kind of design cycles and their marketing cycles. Your new iPhones, they usually come out around the time after the summertime, so that we also have the same kind of requirement, for example, to have our products done before the ramping of their products. If the iPhone comes out in, let's say, September, right? They'll probably need the samples very early in the year, like March or something, so that they can test the chips in their whole system. That means that probably we have to have our design done by the end of the previous year, so that we can have the manufacturability, and if there's any bugs, we can fix them before we ship them to our customers. So that's the seasonability, or the seasonal effect on our jobs. So we have our working peak hours, or we have some a little relaxation hours throughout the year.
Yeah, I guess with regard to preparing for the future, so in 10 years, whenever you guys are going to be thinking about careers and so on, the technology is going to move along. So you're kind of wondering how you're going to keep up with it. What's going to come. But the basic fact is, the way that we deal with information precisely is with math and with science. It's just if you want to describe the world accurately, that's the language you use. If you're talking about how a basketball is going to get thrown, you don't just kind of say, oh, it's going to kind of go over there somewhere. No, you can use math to say, okay, this is the amount that you pushed it, this is the way the air pushes on it, and that's where it's going to land. The same exact kind of analysis you can apply to a circuit. If you want to design it, or any other type of engineering system. So learning the courses you take in mathematics and science, that's just how we generate knowledge. Science is just a process of discovering knowledge. So that will apply regardless of what technology does. So I would encourage you to don't be kind of scared of math. Just give it a try. I personally didn't see the applications for it when you were a student, but in a lot of ways it's really just teaching you how to think. It's not that your job's going to be solving algebra, Although I think I'm one of the very few jobs that actually does have to do algebra, but it's teaching you how to think about the world in an exact way. So if you know, I guess it's kind of early to think, oh, do I want to be an engineer? You know, just because math is not your favorite subject now, and you know you haven't become particularly interested in science or something like that, just give it a try. I'm glad that I did in high school because it gave me a good foundation. But once I got to college, I realized, you know, that this is actually pretty interesting stuff. This is cool stuff. But it sounds like here in Capella, you have some new classes and new opportunities that weren't available to me when I was a student to have these types of discussions and more variety of classes in high school. So I mean, just give it a try. You don't know what you're passionate about until you give it a try.
Do you ever get like to see, like to know what something's gonna look like since you're the one that?
Yeah, we do, and that's a big part of it. Like for example, yeah.
Can you repeat the question? I apologize.
Oh, he was asking, do we get to see what the next generation products are going to be like? And the answer is yes, we do, because if you're trying to design a new product that's going to come out a year from now, the chips and whatever that goes into it, they have to start a year or 2 years or so ahead of time. So in general, you know, you'll have some idea of what the next generation stuff is going to be like, and that's one thing that's really cool. Is just knowing, you know, maybe something you talked about, like for example, that transmission chip. There weren't really any of these dual clutch transmissions around. And then, you know, that's what we heard about from the customer. Hey, we're trying to develop this cool new transmission. It's going to replace the way we do our transmissions in cars or whatever. And then only several years later did it actually become an end product, and now all the cars have that kind of technology in it. It's really cool to think, hey, I was working on that.
Yeah, and I guess another aspect of your question is that now that we know probably what's going to come the next in 2 years, is it okay that we talk about this to our relatives? You know, iPhone is going to be bigger, get it, or something like that. We can't. We basically can't. You know, there's a ethical kind of code in the industry where you're helping the customers to design their system to help them with our microchips to help them implement their whole system. And they gotta let us know what their whole system will be looking like. But it is not okay for us to share this kind of knowledge with other people that are not relevant to the project, basically, or else it's going to cause some problems in the market. You know, imagine that if you have this kind of knowledge from Apple tells us to do this and do that. What if we share the thoughts with some other customers like Samsung? They will take the idea and develop something probably more advanced than Apple, and then when both products are launching at the same time, you can imagine that probably the one who gets the secrets from the other will have more advantage, right?
Question kind of along with that, Will, and that's really good insight. Do you guys have to sign, and maybe you could non-compete, and maybe you can explain that to them as you work on projects? Okay, give them you do a better job than I would. Tell them
a lot of
times.
times.
Well, I was saying, I mean, I guess when you're an engineer, you're working with ideas, right? The value is the idea. So a lot of our customers are the same way. They're coming up with a new way to do a problem. So that's the whole idea of intellectual property. That sounds like an odd idea. How can you own an idea? But we have with our customers, we have to work with them, and usually we have some type of agreement, a legal agreement that we sign that says we won't tell other people what you're doing, and you won't tell other people what we're doing. So that's kind of it varies from customer to customer, but some customers are especially secretive.
Great question.
Do you guys make SIM cards and SD cards?
I don't know if we actually manufacture. Yeah, I mean we don't. No. No. TI makes a very, very wide range of chips, but some companies really specialize in memory, like Micron, for example. All they do is make flash memory. They're really good at it. They have huge factories. TI kind of does a lot of different things.
And I guess SIM card, there's some special manufacturers who are capable to make SIM cards, right?
Yeah, I think so. Yeah, that's a separate. Yeah, I'm not sure if we have anything to do with that or not.
Yeah. Seems the smart ball draws a lot of attention from you guys.
All right, so did I miss when I walked out of the room about our periodic table example?
Oh yeah.
You know that's my favorite part.
Thank you for reminding me that.
I know. So who has the wafer? Hold up the wafer, whoever has the wafer.
Yeah.
Can you guys, do you know what this thing is made out of?
So what materials is that wafer made from? Who can guess?
Actually, this is just inside a little box.
Right. So we've had,
The thing
Did you
inside
guys
the
say
box.
plastic?
we said plastic, copper, iron, titanium are the answers I heard. So, all right.
All right.
So,
All right. So
Roland's gonna
actually,
explain.
it's made out of silicon, which is an element. The periodic table, silicon. And can you guys? This probably since they're so expensive and rare. I mean, where do you think we get the silicon from? Silicon mine, kind of. It's actually
Silicon Valley.
yes, it's made out of pure fairy wood. No, it actually comes from just plain sand, right? Silicon is the most abundant element in the whole mass of the Earth. So we won't run out of silicon anytime soon. Not to say that we don't deposit some pretty exotic materials on top of the silicon, but that's a different story altogether.
All right. So we'll tell them how that happens.
Yeah. So what is sand made of? Basically, it's silicon dioxide. What we use for our wafers and our chips is pure silicon. There is a fab process that where we extract the silicon out of the sands and make it very, very pure. I mean, it is not. This wafer is not going to work if the purity is less than, let's say, 99%, 9999. As long as there's a dust or any not pure particles get onto this wafer, is going to screw everything up. So in the fab, all over the world, the nearest one is actually in Richardson. We have to, the workers in there, the engineers in there have to wear those suits to cover them up so that their particles won't corrupt the wafers.
All right, so when we go to science next time, you're going to look at the periodic table, right? You're going to locate where silicon is, and you now have a new respect for what that does and what we're going to do with sand.
Why do we use? We're getting. Tell us about silicon. Go ahead.
All right. Other questions from y'all? Y'all can't be sleepy.
Silicon is actually not silly. It's pretty smart. That's what we use to implement those smart circuitry on. Basically, physically, what it is. In our world, we have conductors like metals where we can run electricity through it so that we can light a bulb, right? And we also have insulators like the wood in here, like the plastic, so that when you touch a computer, you're not going to be zapped, right? And silicon is basically something in between this kind of two media. That is why it is called semiconductor. What does semi mean? Anybody knows what does semi mean? Yes.
It's like not completely. It's like
Exactly. So, semiconductor is basically half conductor, half insulator, and what we do, if this whole piece of silicon were were fired, or still, there's no possibility that we can make the circuit onto it because the whole piece is conducting, right? And the beauty of silicon is depending on what kind of signal we put onto it, it can turn either into an isolator or a conductor, so that we have a lot of gates which can be interpreted as a lot of switches. And actually, on each one of these little chips in here, little squares, there can be tens or hundreds of thousands of gates in here. And as the era evolves, according to the Moore law, onto this a piece of silicon of the same area, the complexity of the circuit is doubled by every 1.5 years. This is why, you know, like 20 years ago, we had a cell phone like this big, and probably this heavy also. And nowadays, our cell phones are much smaller and much smarter. It has different functionality. You know, it definitely picks up your voice, and it has touch screen, and also it is capable of playing videos. You can play video games in there, and it has different sensors. You know, when you put your phone closer to your face, it's going to dim out, right? And you know, when it heats up, it's not going to work anymore. It's not going to consume more energy. For example, if you leave your phone in your car in the afternoon and going to the zoo, when it is charging, the car itself will heat up a lot under the sun, right? So when it reaches a certain amount of temperature, the charging capability is disabled. So I mean, the cell phones or the electronics are made much smaller nowadays with more and more functionalities. That's how the technology is evolving. Any other questions? Yes, sir.
What does the sand become after you take the silicon out?
It has a
Oxygen.
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 Well, I guess there's a lot of, I mean, just crude sand has a lot of other stuff in it too.
Yes.
But, you know, silicon dioxide is a big component in sand, and they can refine it out of there. And they have a process to basically pull the oxygen off of it, right? And it's actually kind of a cool thing because that's, the wafers come from a large, you know, chunk of silicon, but that's actually one single crystal. If you think about a diamond is a crystal, right? It's a uniform structure, whereas something like concrete is a bunch of little bitty crystals mixed up. The silicon that this comes from is, I think that's one of the main innovations that allow this kind of stuff, is actually one single crystal, and it might weigh a couple of 1,000 pounds, and it's like having a diamond that's this big, and that's what they use to cut it with, and all of the atoms in the crystal are lined up in a perfect way. So it's pretty amazing.
Yeah, I guess a good analogy of how people get the oxygen out of the sand is probably, you know, when we have a bottle of water and we have 2 electrodes into it, and if we kind of run electricity into the water, there's a process that, you know, the water can be separated or can be dissected, and out of water you get hydrogen and oxygen. So these 2 elements are separated, and so that's what is it called?
I guess you would basically melt the sand.
Yeah.
Right. Yeah, that's what you learn about that in chemistry class. When something oxidizes, it gives off heat, so you have to give it energy to try to separate it again. Things want to stay in an oxidized state, so usually when you heat it up, you melt it. You'll kind of wiggle the atoms enough that they'll break apart.
With TI being a worldwide company and you two both being based here in Richardson and having clients in different time zones all over the world, how do you accommodate that in your schedules, and how do you meet with other team members who aren't in the same physical location or time zone?
Yeah, I interface with the customer a lot. A lot of our customers are in Asia, in China, in Taiwan, Japan, and some of our customers are in Europe, in Germany, in France, in England. So a lot of the times we have to go out there ourselves to pick up, you know, what their thoughts are, you know, what kind of problems they're trying to solve. And a lot of times we have to do conference calls, meaning that we'll probably cope with the schedule, time difference between different countries. For example, right now we are 3 p.m. In the U.S. or in Dallas. It's right now probably, you know, 5 a.m. over in China. If I want to solve a problem with the Chinese customer, is it okay that I call them during their midnight? No, it's not, right? So we usually work out a schedule that we can work together to complete the conference calls and customer visits.
You both being different types of engineers or engineers, do you find is your job one in that we've worked on individual projects in our class, and then we recently did a group project too, so we saw the benefits and the difficulties in both. Do you generally work alone in the tasks that you're day to day, or are you part of a team, or maybe you can tell us how that works too?
Yeah, I mean, we're very, very much a part of our team, of a team. I guess we have to work with people all the time. I think the nature of it is a little bit different because there's no way that you could do everything that TI has to do as one person. You have to rely on other people to do their jobs, and you have to do their jobs. So, you know, that's how it works. There's no way that you can all do it together. So that's an important skill you can learn here.
From the group projects.
Yeah. So, but ultimately, you know, especially in my job, you know, a lot of it is spent, or maybe half the time I spend thinking myself how to solve problems, working through solutions, and the other half I spend interfacing with colleagues, having whiteboard discussions, going through new ideas, and also meeting with customers.
What do you like most about your jobs, and what do you like least about your jobs?
What do I like most? I just like that there's always, you know, at least for maybe 6 months out of the year, there's some kind of new problem that I don't know how to solve. That it's not like I'm bored. I have to, you know, I don't know what to do. I need to go learn something. I might need to go read some papers. I need to go talk to my other colleague in a different group and learn something I never knew before. I think that's the coolest thing. Is just, you know, as the more you know, the more you figure out you don't know, and it's just kind of you learn to appreciate knowledge, and engineering gives you an opportunity to meet a lot of really smart people and learn a lot of stuff that you wouldn't learn otherwise. What do I dislike? I mean, you know, it has some long hours, and sometimes the product cycles, some parts of it are less fun than others. You know, I like designing the chips. I don't really like, you know, trying to make sure that they're super high quality. Well, they need to be high quality, but I'd say that, you know, just there's some parts that are more routine, you know, that are going to be effective for any job.
Yeah, I like my job because I'm the type of person who likes to talk to people, get their inputs, seeing what they are thinking. You know, to have communication with the customers. That's the favorite part of my job. And what I don't like about my job is probably 7 a.m. call in the Monday morning with customers.
As we try and find a work and life balance, do you guys find that difficult in your jobs? Meaning, obviously, we've talked a little bit at lunch, and I know you're both married and so forth. Do you find it difficult based on the number of hours you work, or have you developed something that is a happy?
Well, I would say engineers just have you'll find that they want to work almost, but at TI, you know, they encourage and they give time. You know, you have time off. They encourage you to do things like volunteer and get out there and just have a life aside from working. I mean, you need to do that to stay sane anyway. So sometimes you're very, very busy on a project, like with the product cycles, and maybe there's some kind of a problem, and you'll be pretty much living and breathing chips. But other times it'll slow down more. You'll have time to kind of, you know, to do other things. So there's a decent work-life balance, and you're not stuck to like, you know, you're not going to be called in the middle of the night like a surgeon or something like that. It's usually pretty regular hours and very what they call results-based, which is you have a problem to solve. You need to have it done by a certain time, but you're not, you know, you might have you might do more in 1 hour than you might do in 8 hours the next day just because you have an idea. So it's kind of different. It's just a different kind of thing. It's not like you're trying to, you know, stamp something all day long and you're going to have a certain amount that you're going to finish. You know, it's less defined time-wise. So that's something you kind of get used to. It takes. When I first came out of school, I was so used to having it like, oh, it's the next class. Oh, it's the next class. Oh, I got to get it done. My homework's due. But at work, you know, there's not a definite line. It's just, hey, you need to figure this out however you need to. You know, you need to tell me how long it's going to take you to do it. It's just a readjustment, but it's also kind of liberating because then, you know, you're going at your own pace. Well, of course, there are customer schedules.
Yeah. I guess.
So how can y'all, I'm sorry, Will. How can y'all connect what Roland just said to how we do our projects? So if Mr. Stewart and Ms. Goodman are the customers, and we've now said that we want this presentation to be due on November 4th. It's the same kind of concept, isn't it? So how can you help me
Like,
explain that?
if maybe like one of your group members needs to finish something up and you ask them how much time they need to finish it up and maybe like ask them to do it at home or.
Right. Yeah, so that's a very good example. So you're working within your groups. They work the same thing with their groups. So we're doing the exact same process that they're doing in their everyday lives. And for their employers, they have their customers. Mr. Stewart, Ms. Champagne, and Ms. Goodman would be the customers in this situation. And we've said that this is the result that we want. So we're still doing result-based work, right? So this is the result we want to see. And this is the due date that we're kind of expecting you to accomplish it by. So y'all now work within your group and decide how you're going to problem solve, who's going to take each role, who's an expert at what. You did your true colors. You know how you can work with somebody that's a blue or an orange or a green or a gold and what their strengths are and how you can bring that strength out of that group member to be able to excel and get to the next step. And just like her example, you know that somebody might need to communicate how long it's going to take for them to finish that portion of the project so that you can finish the next step in that project. So it's the same thing that happens every day for everybody that goes to work. Your parents, Mr. Stewart, Ms. Champagne, and I, we even have the same problem solving that we have to do when we're setting up our lessons for y'all. So it's the same skill that we're rotating through every single time we do a project, that you're going to transfer that skill into the workforce. Right now, too, we're working on social skills, right? So one of our big taboo questions that we talked about that Roland and Will had already prepared in advance for us was that we don't want to say, Mr. Sun, how much do you make at TI, right? That's not a question we want to ask. So how would we rephrase that question if he hadn't already told us what the salary ranges were? How else would we ask that question? Who can help me? Leo.
What is like the average person like that makes, or how much you make in like the TI program or any type of like specializing on the
Right, very good. So what would be the average salary for this job description? What would be a salary range that we can get from working at Texas Instruments? What would be a starting salary right out of college that we might have an expectation for? What would be a salary for our region? So those are the ways that you will be able to present those questions to our future speakers as well. So all of these things that we're teaching you in IExplore are going to be able to transfer right into the workplace and right into everything that Roland and Will have described to us. So very good. Thank you for input on that. We have 4 minutes. Did we have any other questions?
I think the coolest thing that I heard, and I didn't hear it till this period, was, at least to me, it resonated with, is with, these guys are part of a team and it's cutting edge stuff that they're working on, right? They are seeing pieces and prototypes of stuff like the next generation phones before they come out and hit the public. How many of you have ever gone to, the Dallas Car Show or something, and they talk, here's a prototype that's going to be out in years from now. These are the kind of gentlemen and experts right here who are seeing that and are behind the scenes from a technological perspective related to semiconductor. As Will said, these are so, top secret, if you will, that when they go in with team members of their clients, they're having to sign a legal document that says, do not share this with anybody, because the last thing we want to do is have a competitor get out there and get wins so they can compete against us. So there's a lot of cool things about this, and that really resonated with me as you said that today. So thank you.
Yeah, thank you.
Any other questions as Mrs.